In our last video for chapter 19, we will be looking at conjugate addition, which is nucleophilic addition to an alpha-beta unsaturated aldehyde or ketone. So here we have an example of an alpha-beta unsaturated aldehyde. This is an aldehyde, and if we focus on the carbonyl carbon, the one adjacent to it is the alpha position, and then the one next to that is the beta position. Because we have a double bond, in other words, we don't have the maximum number of hydrogens, this is alpha-beta unsaturated. This is a conjugated system where the oxygen, carbon, carbon, and carbon are all sp2 hybridized, and that makes possible resonance. So any carbonyl, we can have resonance that looks like this. And this resonance contributor is one of the reasons why the carbonyl carbon is electrophilic. But in the case of the alpha-beta unsaturated aldehydes and ketones, there is another resonance contributor. So if we imagine these electrons move here, we have this. Try that again, because we have the negative charge on the oxygen and the positive formal charge here. So the resonance hybrid of an alpha-beta unsaturated aldehyde or ketone will have partial double bond character between these carbons and these carbons and this carbon and oxygen. We're going to have partial negative character here, but what's probably most important as we think about reactions is that we have partial positive character here and partial positive character here. That means we have two sites on this compound that are electrophilic. Let's see how alpha-beta unsaturated aldehydes and ketones compare to other alkenes and to other aldehydes and ketones. In general, alkenes are electron-rich, and so they can act as nucleophiles. But an alkene that is conjugated with a carbonyl, because of this resonance structure, that means we have a partial plus on this carbon, which means that this alkene is not as electron-rich as this alkene. And so this compound will be less nucleophilic than typical alkenes. When we think about an aldehyde or a ketone, we know that this carbon has a partial plus, and so it can act as an electrophile, as we've seen many examples where a nucleophile can share electrons with the carbonyl carbon. Well, in the case of a carbonyl that is conjugated to an alkene, we have partial plus character at this carbon and partial plus character at this carbon. Now, it is possible for a nucleophile to share its electrons here, pushing these electrons up onto the oxygen, and this is called 1,2 addition. Because we are thinking about the oxygen as position 1 and this carbon as position 2. It has nothing to do with IUPAC naming, but the carbonyl oxygen is called position 1. Now, it's also possible for a nucleophile to add to this carbon, which pushes these electrons here and then these electrons up onto the oxygen, and that is called 1,4 addition. Because if we continue counting, we have carbon 1, 2, 3, and 4. So having an alkene conjugated with a carbonyl makes this compound behave differently than other alkenes and behave differently than other aldehydes and ketones. Let's take a look first at 1,2 addition. So if we have a nucleophile and it shares its electrons with this carbon, that will push these electrons onto the oxygen. So that will give us this intermediate, and then the O- can grab a proton from H3O plus or from the solvent, and you end up with an alcohol. So this is the 1,2 addition product. Now if we consider 1,4 addition, let's say that our nucleophile adds to this carbon, pushing these electrons here, pushing these electrons here. That gives us our nucleophile connected to this carbon, single bonded to this carbon, double bonded to this carbon, single bonded to the oxygen, and here is our hydrogen. So we have this intermediate. From here, we have two options. One is that the O- could grab off a proton from here, and that would give this, which is an enol, because we have an alkene and one of the alkene carbons is connected to an alcohol. The other possibility is that these electrons come back in to reform the carbonyl, and then these electrons grab a proton. That gives this as our product. While this is an enol, this is called the keto form, even though it is an aldehyde. A carbon-oxygen double bond is stronger than a carbon-carbon double bond, so this product is favored instead of this one. So with 1,2 addition, the nucleophile adds to the carbonyl carbon, and we end up with an alcohol and a new bond between what used to be the carbonyl carbon and the nucleophile. For 1,4 addition, the carbonyl is restored at the end, and then alpha beta position has a new bond to the nucleophile. Different types of nucleophiles tend to undergo 1,2 versus 1,4 addition. Let's look at some examples. If we have cyclohexenone and we treat it with a Grignard reagent, we are going to get exclusively the 1,2 product. After step 2, H3O+. If we use cyanide, here we are going to get the 1,4 addition product, and with something like an amine, rather than forming the imine or the enamine, we tend to get the 1,4 addition product. So, what is the difference here? We know that a Grignard is a source of a nucleophilic carbon. We also know that CH3- is a really strong base. So, once the Grignard adds to this carbonyl, this reaction is not going to reverse. Cyanide or an amine, these undergo reversible nucleophilic addition reactions, and that is an important distinction. Let's draw an energy diagram for 1,2 and 1,4 addition. So we're going to have our starting material in the middle, and we can have the reaction going in two different directions. So if we have 1,2 addition, then our intermediate is going to look like this, and then our product is going to look like this. These are intermediates, which means that we have a transition state leading to that intermediate, and then a transition state leading to this intermediate as well. Or we can have 1,4 addition, and this intermediate would look like this, and then this product would look like this. So activation energy getting to the transition state, and then there's some transition state bringing us to this product. Now, I'm not sure about the relative energy of the starting material compared to the product, and that's not what I'm trying to show. But what I do want to focus on is the relative height of the 1,2 product compared to the 1,4 product, and the relative height, the relative energy of the 1,2 intermediate compared to the 1,4 intermediate. This is the activation energy of the rate determining step for 1,2 addition, and this is the activation energy for the rate determining step for 1,4 addition. This arrow is smaller, which means the red reaction is going to be faster than the blue reaction. So this tells us that 1,2 addition is faster than 1,4 addition. But if we look at our products, the product of 1,2 addition is higher energy than the product of 1,4 addition. So the 1,4 product is more stable than the 1,2 product. So we talked about this type of situation when we talked about kinetic versus thermodynamic control. In some cases, the kinetic and thermodynamic products are the same. In some cases, they're different. In some cases, it can be controlled by changing the temperature of the reaction. And in some cases, it's determined by the nature of the reagents. Any nucleophile that is going to add, it's going to go the red way. So a nucleophile will add 1,2, giving the 1,2 product. Where the difference comes in is, after this happens, can the reaction go backwards? In other words, if a reaction is irreversible, the reaction will go the fast way and then it'll stay there. So when it's irreversible, you will get 1,2 addition. When the reaction is reversible, well, it's still going to go 1,2, but then the system has a chance to equilibrate to lead to the more stable product. So if the reaction is reversible, then you're going to get 1,4 addition. Now let's look again at this slide. When Grignard was used, we got the 1,2 product because Grignard will add 1,2 and then it's not going to reverse. And so what will be isolated is the 1,2 product. Cyanide is a much weaker base, so it will still add 1,2, but then it can reverse and then add 1,4, leading to the 1,4 product. An amine is also a weaker base, so it will add 1,2, but then it will reverse and it can add 1,4. So strong bases such as a Grignard or an organolithium, these are going to give exclusively 1,2 addition products. Weaker bases such as cyanide or amines, these are going to give the 1,4 addition products. Now let's come back to our old friend, a lithium dialkyl cuprate. So we saw this a few chapters ago, and if we have a lithium dialkyl cuprate, this can react with an alkyl iodide or a phenyl iodide. There's some flexibility with the coupling partner, with the Rx. It works best when this is methyl or primary, but yet you're still allowed when you've got a phenyl. Go figure. What's going to happen is that this will couple with this. So here we will get phenyl CH2, 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 CH3. Alternatively, we could accomplish the same thing in the other direction. If we had the lithium dibutyl cuprate and reacted it with phenyl iodide, then we would get this, which gives us the same thing. Well, now we're looking at cuprates again, talking about reaction with aldehydes and ketones. If we have a regular aldehyde or ketone and we treat it with a cuprate, we will get no reaction. But if we react a cuprate with an alpha-beta unsaturated ketone, not aldehyde, but ketone, we will get the 1,4 addition product. So we will end up with this. The mechanism is not the same as what we just talked about with cyanide or an amine doing 1,2 addition and then equilibrating to the 1,4 addition product. This goes through a different type of mechanism. You're not responsible for the mechanism, but think about the value of this. If we have an alpha-beta unsaturated ketone and you want to add an alkyl group 1,2, then you would use a Grignard reagent. But if you want to add it 1,4, then you can use a cuprate. So you have a couple different ways to add alkyl groups or aryl groups or vinyl groups. And by selecting the correct organometallic version of a particular group, you can control whether you get the 1,2 product or the 1,4 product. So we've seen a lot of reactions to form aldehydes and ketones, but especially a lot of reactions of aldehydes and ketones. It's important to be able to separate the irreversible nucleophilic addition from reversible nucleophilic addition and think about what that means in terms of equilibrium. We've seen other valuable reactions of aldehydes and ketones such as the Wittig, and now we've seen conjugate addition reactions to alpha-beta unsaturated aldehydes and ketones as well.